please. Next slide. So we can also show that these subsampled random forests are a special kind of U statistic. So on the left, if we define this U statistic, you can see that the kernels are just the trees from the random forest estimator. So this itself is the random forest estimator. And since we are averaging over BN trees and not every possible subset from our sample, it's an incomplete U statistic. And also, since the trees are each dependent on their own randomization parameter, it's a random kernel U statistic. And also, since each tree is dependent on the subsample size, which is growing with n to infinity, it's an infinite order U statistic. And even though this U statistic has all these special kind of properties, we can still show that it has these similar asymptotic properties. So on the right, we can see that this U statistic, which is just the random forest estimator and its predictions, is asymptotically normal. Next slide, please. So since we now know the asymptotic distribution of the random forest, we can try to estimate the asymptotic variance. And we can do that using the infinitesimal jackknife, which is a version of the ordinary jackknife. But instead of omitting one observation at a time, we just assign each one a weight and slightly downsample each observation, or downweight each observation by an infinitesimal amount. And then as we let the number of trees go to infinity, this is our infinitesimal jackknife estimate on the left, the expression. And then given the same convergence and error conditions as on the last slide, we can show that this infinitesimal jackknife estimator is consistent for the asymptotic variance of the random forest predictions. And this is really useful for confidence intervals and also testing feature significance. Next slide. And that's all, thank you.
Thank you, Candace. Very nice talk. Shinjo, please move on to the next deck of slides. Yeah, very nice presentation. I just want to say that probably in your report, please emphasize that here the U statistic is about the prediction. So the statistic itself is the output of the random forest. And I think here they are doing the regression problem, if I'm right, not the classification problem.
Yeah.
Okay, thank you. Thank you, Samantha. Now it's your turn.
Hi. Am I audible?
Yeah, please go ahead.
All right, so today I'm going to talk about the application of asymptotic theory in horizontal gene transfer because it's like of particular interest to me. Next slide, please. So I'll be talking about what horizontal gene transfer is, and then the three approaches that I'm going to kind of like briefly go over. Next slide, please. Okay, so horizontal gene transfer is like usually bacteria grow vertically where like the parent gives the offspring, and that's how the genetic material kind of moves forward. But in horizontal gene transfer, you can pick up genetic material from your environment, or like a virus could attack you, or as we see here in this slide, you can take the genetic material from another bacteria by creating a pilus, which is kind of like a bridge between the two bacteria. And because of like these different kinds of ways HGT like expresses itself, it can be kind of complicated. So for like convenience purpose, we are only going to look into the conjugation part. In conjugation, we see the F plus and the F minus over here, which is basically the plasmid, which is being transferred, and that contains the genetic material from the F plus bacteria to the F minus bacteria. So in the end, they both become F plus, and they both have antibiotic resistant genes in them. Next slide, please. Okay, so when you have like a bacterial population, there are a host of interactions that could happen where two F plus bacteria could interact, or like an F plus and F minus can interact. So like in the end, you both have like F plus, or like F minus and F minus can interact, and that doesn't usually like kind of yield anything for us, but we must consider all of those. And also at the same time, we must also consider the viability of the bacteria itself, if they can carry out the metabolic processes that are involved in transferring the genes, whether or not they're resistant. So considering all that, we have the probability PV, PC, and PR. So PV is like the probability that the bacteria is viable, and PC is whether the conjugation like actually takes place, and PR is like resistance proportion, like how resistant, like how resistant the other bacteria can become because of this transfer. And here we also have alpha. So there's alpha V, alpha C, and alpha R, which again like corresponds to the three probabilities. And the L would be the length of the genetic material, and rho is the population density, which will remain constant because we're assuming that the volume will also increase with the population, and like the density will not change, which is important because going forward, because we will be looking at the product of rho and gamma, and when it varies, it basically means that the gamma is varying because the rho kind of remains constant. And KT is the mean fitness of the population, or the first order growth constant, which is our prime focus here. Next slide, please. So after doing a bit of like simplification, there are two regimes that we come across. One is when the KD, which is the decay constant, which will remain constant, but in that case, the gamma rho will keep changing. So it could either go towards zero or it could go towards infinity. And like you will have a transformation like term for each one of those. Sorry. Okay. So each one of those will have its like own terms, and that after simplifying that, you will come to the final equation. Next slide, please. The first graph here shows when the gamma rho keeps changing, but the KD remains constant. And the second one shows where the KD is varying, but the gamma rho is like, so the gamma rho is constant, but the KD varies. And here, where there's no conjugators, it means the KD is zero and like they're all dead. And conjugators means like the KD keeps like asymptotically increasing. Next slide, please. So finally, we arrive at this equation, and the solid line is basically like the numerically solved version of this equation. And the dotted line is, I think the dotted line is the one where the KD is constant, and the dashed line is when the gamma rho is constant. And it kind of gives us like an overlapping, this final solution just shows the overlap between the two regimes.
So Samantha, sorry for the interruption, but your time is up.
Yeah,
can you quickly wrap up? Yeah, in like 10 seconds.
Okay, so yeah, this is what happened in this like and I had two more, but then I guess like it's of no use because I took too much in this one.
Yeah, my suggestion is that your work, this self-service seems to be very dense, especially for people like me who didn't know this field that well. I would suggest that it's very important for you to emphasize the big picture and why we want to do this, and which part of this equation derivation did asymptotics help. Just point out those key points in your report that can help me better understand what you mean. Thank you.
Thank you.
Thank you. Yeah, let's move on to our next speaker.
Hi, good afternoon, everyone. I'm Shu Wang, and today my topic is asymptotic notations in asymptotic analysis of the algorithms. So in our first lecture, one just talk about the asymptotic notation like the small o, the big O, the same order, and the asymptotically equivalent. I was fascinated by these notations. And I would like to do some research to trace back to the history and the development of these asymptotic notations. And I also want to know the current situation of these asymptotic notations in the computer science and the statistics. So that's my today's survey topic. Next slide, please. Okay, cool. So here is the reminder of the lecture notes. So on the first lecture, we talk about the asymptotic equivalence, like if an is asymptotically equivalent to bn, that means the ratio of an over bn is will converge to 1 as n equals to infinity. And we also talk about the same order. And after that, we talk about the small o notation. So if an equals to the small o of bn, that means that the ratio of an over bn will converge to 0 as n goes to infinity. And also, we talk about the big O notation. So the big O is the same small o plus the same order. So the big O indicates that the so if an equal to big O of bn, that means that the bn is an asymptotical upper bound on an. So after we learn that, I do some research to study the origin of this asymptotic notation, and I found that in fundamental algorithms written by the Donald Knuth, he traced the origin of the big O to the book that analytic number theory that is written by a German mathematician called Paul Bateman. And after that, the small o notation was invented by the Landau in his book, Handbook of the Doctrine of the Distribution of Prime Numbers. And several years later, the big omega and the big theta notation were also invented. They are advocated by the Knuth in his paper, Big Omicron and Big Omega and Big Theta. Knuth tried to write this paper to correct the popular but technically sloppy practice in the literature of using big O for both upper and lower bounds. So in my report, I will make some comparison about these notations in different phases in history. And here I list several, 5 notations in current computer science. When we try to analyze the growth of the function, when we analyze the asymptotic efficiency of the algorithm. So this is the definition of the big O notation. And the big O, normally we use it as an asymptotic upper bound. Next slide, please. Here, there's some typo, but this slide I try to define I try to write down the definition of the big omega. So the big omega is for the asymptotic lower bound. Next slide, please. And this is for the small omega, or small o, sorry. So the small o is an upper bound that is not asymptotically tight. So the difference between the small and the big O in this formal definition is that you can see that the small o, it is for any positive constant C, but in that big O, that the condition is kind of loose. It requires there exists a constant that C is greater than 0. So that's the main difference. Next slide, please. Okay, so this is the last slide. So this is the small omega. So this is notation. This notation is used for define the lower bound that is not asymptotically tight. And next slide. And this big theta is asymptotically tight bound. So we also have a theorem that talk about 2 functions when they can be when like g of n is asymptotically tight bound for Fn. So it should be satisfy these conditions. Next slide. Okay, so that's all. Thank you for listening.
This is a very interesting introduction, Shu. I think many of us, this is very new to us, the historical review. And I just want to point out that, so please make sure that in your slides, there are a few typos, right?
Yeah.
The title, you had one thing, but the formula has a different thing. Please make sure to correct those in your report. Since here you have many notations and they mean different things, slightly different things. So it's very important that you have them correct, the notations correct. And also, I think it's very important that you make some connection to the notations we introduced in the class. So for example, I can see that the theta notation is actually quite similar to our same order notation, right? It's quite similar to that. So you can make those connections in your report.
Sure.
Thank you.
Thank you.
Okay, our next speaker is Wenbing. Please go ahead.
Hi everyone, can you guys hear me well?
Yes.
Okay, so today I'm going to give a presentation on canonical correlation analysis, which I use quite a lot recently. And please go, yeah. So this presentation will be divided into two parts: the introduction and then the derivation of canonical correlations. And the third part is a sample estimate. And the fourth part is related to the asymptotic distribution, which is a hypothesis testing for selecting canonical weights. Next slide, please. Yeah. So as a brief introduction, this canonical correlation analysis is proposed by Dr. Hotelning in 1936. So it's quite a long time ago, but this one is quite useful in the multivariate analysis. Still till now, we have a very wide application in economics, in education, and also in the genomics. So this one is to find, aims to find the linear relationship between two vectors of variates. Here I noted them as x and y. X has a p variable and y has a q variables. So the dimension can be different between x and y. And this approach is trying to construct a canonical variance that maps the x vector to a single variable and the y vector to another single variable omega by a linear combinations. So the canonical correlation is defined as the correlation between this psi and omega. Next slide, please. And so this is about the derivation of this correlation. So consider arbitrary linear projection, and without the loss of generality, we assume that psi and omega will have a mean 0 and variance 1. And then the canonical correlation can be just directly write as the G transpose times covariance X, Y, and H. So our goal is to find G and H to maximize this correlation. Next slide, please. And so how to find the maximal correlation? So they use a technique of Lagrange multiplier. So basically we construct an object function which shows F and G and H here. And we take the derivative of, with respect to G and H, so that we can get this this equation. And so if we cancel the variables, for example, cancel lambda and mu, well, we can basically generate. We can basically see that because the G transpose covariance X and X times G is equal to 1, so we can get the following equations, and then the original combined with the partial equation, partial derivative equation, we basically trying to solve the last equations. Next slide. And so this one can be rewritten as this first formula form. So basically, we found that it's very interesting that for the left factor, it's basically just an eigen decomposition of the R matrix. And if we take that lambda equals lambda 1, which means the biggest eigenvalue, we can write out the H and the G, and then we directly found that this correlation between canonical variables is just the first eigenvalue. And so if we have multiple eigenvalues, for example, lambda 1 squared to lambda s squared, s here means the degree of freedom. So these eigenvalues will directly correspond to the canonical correlations. Next slide, please. And so for the sample estimate, it's quite straightforward that we just replace the original population covariance with the sample level covariance matrix. And then we can do the eigen decomposition on the R. And then we can directly calculate the lambda J and also get the canonical covariance. Next slide, please. So one interesting topic about this canonical correlation is about the variant selection. So basically this one canonical correlation analysis can be served as a dimension reduction technique. So for this row here, the canonical correlation, we want to know how many canonical variable we want to keep. So here we assume that starting from k plus 1, the null hypothesis of the canonical correlation.
Sorry for the interruption. Wenbin, your time is up. Let's quickly wrap up in 10 seconds.
Yes. So this one will be 0, and so under the normality assumption, the likelihood ratio statistics will be can be written as this. And so in Bartlett derivation, we found this when n equals large, this can approximate to the chi-square distribution. And yeah, let's basically work for my presentation.
Yeah, very nice talk, Wenbin. I just want to make a point that there might be a typo in a previous slide where you showed that lambda square corresponding to rho square, but I think it should be lambda that corresponds to rho square. So just check that later.
Oh, yes, thank you. Thank you.
Okay, yes, so, okay, let's move on to our next speaker, Hao.
So I haven't received the slide from Hao.
Is Hao here? I don't see him here. So in this case, let's move on to our next speaker, Hongda.
And we also
okay. Okay, then let's move on to our 7th speaker, Zihan.
Hi everyone.
Hi, please start.
Hi everyone. Today I'm gonna present the summary on the sampling insights in using the central limit theory in the gamma distribution. Next slide, please. So the central limit theory is the most fundamental theorem, and it is a cornerstone in the modern statistics. So let's record the central limit theorem first. So the random sample x1 to xn are IID with a finite mean, mu, and a finite positive variance sigma square. And the xn bar is the mean of the x1 to xn. Then the distribution z is sigma square root n times the xn bar minus mu will converge in law to a normal distribution with a 0 mean and sigma square variance. And the central limit theorem can express as this. And when we apply the central limit theorem, we just assume the n will goes to infinity. However, in the practice, we probably cannot get a sample mean with the infinity sample size. Next slide, please. So we probably have a question saying that, so what is the criteria for applying the central limit theorem in the practice? So Plan and Gordon in 1982 claimed that the sample mean xn bar can be assumed as a normal distribution as long as the sample size n is greater or equal to 30. But Hongqu Zhang et al. 2008 believe that that criterion is not convincing and might not be feasible for every distribution of the population. And because they thought that different distribution will have the different shapes of probability, like single peak, multi-peak, symmetric and asymmetric, like high skewness and low skewness. So the xn bar from the different distribution will probably have the different approximated speed toward the normal distribution as n increase. So they trying to figure out how fit that criteria is for the gamma distribution. And they also expect to find out the least required sample size for the gamma distribution. And they used the numerical simulation techniques to achieve that. Next slide, please. Then I just will summarize their paper from the next following 3 parts. Next slide, please. And the simulation and the statistical test. They choose the standard gamma distribution as their object of interest by setting the beta is equal to 1 and the gamma is to 0. And the probability function is here. And they also use the Shapiro-Wilk W test to test the normality of each sample mean. And the W test is showing here. Next slide, please. And basically they just draw 1,000 random sample of the size n from the standard gamma distribution for each parameter alpha. And the n is from 2 to 150 and the alpha is from 1 to 60. And therefore they result in 8,940 groups of generated sample means. And each group will contain 1,000 sample mean, like can be denoted as xn1 bar to xn1000 bar. And then they just use the Shapiro-Wilk W test under the significant level 0.05 for above the normality of the sample means. Next slide, please. And so for each test, one outcome will come out like either accept or reject the normality, and they just repeat the test 100 times for each sample mean. And they define the success is that the test does not accept the normality hypothesis. And at the same time, they just define M is a number of the success. Next slide, please. And then they just summarize their test result as shown here in this plot. It is also describing the relationship between the rejected frequency and the sample size here. And so obviously we can see that sample size n and both sample size n and the parameter alpha will have the significant effect on the normality of the sample mean. So they're trying to find out the relationship or the chain between the rejected frequency m and the sample size n by establishing the inverse regression model as shown here. Next slide, please. And they just do the regression, and this table is showing the result of regression. So obviously we can see that the R square value increases significantly as the alpha climbs from 1 to 17. And after that, the R square value just falls down all into the longer and flatten the tail of the function at larger alpha, as you can see in this plot. And next slide, please. And they also define the different required level M prime for the result of the frequency of the normal test. For example, the M prime is equal to 5 means the rejected frequency M is less or equal to 5. So they are interested in the required level M prime is equal to 5, 10, and 20. And they also want to find the chain between the sample size n and the parameter alpha by establishing the similar inverse regression model and do the regression. The regression result is shown in this table and this plot. So in this way, they can try to find out the least required sample size for each parameter under the different required level M prime. Next slide, please. And this table is showing the least required sample size n for each individual parameter alpha under the different required level. As we can see that larger like parameter alpha, it will make the central limit theorem more feasible to apply because it requires smaller sample size to satisfy the normality of the sample mean. And secondly, the previously suggested n equal to 30 is not feasible for the next like following 3 scenarios, like parameter is less or equal to 15 under the M prime equal to 5, And for the alpha is less or equal to 7 under the m prime equals to 10, and alpha is less or equal to 3 under the m prime is equal to like 20. And thirdly, when the alpha equal to 30, the least required sample size n under the m equal to 5 and 10 are just only 21 and 10 respectively. They are all less than 30. Next slide, please. So basically we can just summarize the conclusion here. The first one is that the various distribution will have the different like approximated speed towards the normal distribution of the sample means. Therefore, the least required sample size for the normality would vary. They could either be like greater than 30 or like smaller than 30. Secondly, specifically for the gamma distribution parameter alpha will have a significant effect on the normality of the sample mean, and larger alpha value requires a smaller sample size to feed the normality of the sample mean. Next slide. That's it. Thank you so much.
So thank you, Zehan. So my only comment is that your talk is based on one paper mostly. So I would suggest that as a survey paper, please also include some other references, maybe borrow some other information to support the conclusions in this paper so that your paper will not be just based on this one paper.
Okay.
Okay.
Okay. Thank you.
Melody, please start.
Hi, I'm Melody. Today I'm going to talk about the asymptotic efficiency gains from design-based considerations in experiments with low rates of compliance. And so this is based loosely on a paper that I'm working on with my advisor, as well as a lot of literature in the blocking and post-stratification world. Next slide. So to start off with some context, randomized controlled trials are a powerful tool to estimate causal effects. Researchers tend to like experiments because they're able to randomly assign treatment to the units in the experiment. And so when that's the case, we can leverage the fact that you don't need many identifying assumptions in order to estimate the causal effect within a given experiment. However, usually when we talk about estimating the causal effect in an experiment, we assume that everyone we assign treatment to takes the treatment. But in practice, that's not always the case. And so whenever there is non-compliance, which is what we call when units assigned to treatment don't necessarily take the treatment. So whenever there is non-compliance, we can no longer identify the average treatment effect from randomization alone. And that's because there tends to be a confounding effect from those who comply. And so like the compliance status of an individual will affect the outcome. And so to make this a little bit less abstract, you can consider the example, like let's say you work at Google and you want to see whether or not a feature on an app is going to increase usability. So you deploy this feature to half of your users, but only a very small percentage of them actually opt in to take it. They might not necessarily be representative of the average user that you're interested in looking at. So instead, when there is non-compliance, we have to estimate something known as the complier average causal effect, which is basically the causal effect, but over just those who comply. Okay, next slide. Okay, and so the motivation for looking at this in the context of this course is that as more experimentation takes place online, researchers actually have a greater capacity to recruit huge experimental samples now to like run experiments on, especially if you work at a tech company, your user base tends to be large enough to where you do care about asymptotics. And so in those cases, while N is really, really large, compliance rates are very, very low. And so current estimation approaches rely on post hoc adjustments. And so a common approach is using instrumental variables, which was developed in the 90s. And that works well, except it is a function of 1 over the probability of compliance. And so when compliance is very low, the precision of this estimate tends to deteriorate and you have huge blow up in variance. A second set of estimation approaches relies on the principal stratification literature, and this uses weighting. So we basically estimate the probability of compliance across all of the units using pretreatment covariates and then reweight the data so that we can estimate case. The drawback to this is it relies on stronger assumptions. And so when those assumptions aren't met, the estimates are biased, although this tends to do well precision-wise. And so a proposed approach is to leverage a blocked experimental design in order to account for these pretreatment covariates at the design stage to produce more precise estimates without invoking stronger assumptions. And then the goal is to examine the asymptotic efficiency gains that can be found from using this design-based approach to estimate case. Next slide. So I don't have time, since it's a short presentation, I'm just going to go over the key takeaway, which is that we can compute the asymptotic relative efficiency of using this blocking approach over the post-hoc approaches. And we're going to find that it's going to depend on two quantities. One is going to be the intra-block variation, and the second is going to be the inter-block variation. And so what that means is, if we look at just the blocking literature, a lot of it, blocking tries to minimize the inter-block variation. So within the block, you want as little variation as possible. And by doing so, it maximizes the intra-block variation, so the variation between the different blocks. And so depending on how well those covariates are able to explain that variation, you're going to get different asymptotic relative efficiencies. And so I've simulated two examples here. The first one on the left uses covariates that are highly explanatory of the outcome. And so the blocked difference in means estimator is the pink bar on the leftmost. And so that's 1, right? Because we're dividing each by 1. And so here we're looking at the asymptotic efficiency of all these different estimators, and we see that IV does the worst. So we're able to improve most off just instrumental variables, and it outperforms certain principal score weighted estimators. And on the right, we have an example in which the blocking variables are less explanatory, and so the asymptotic relative efficiency is less good. And so in the paper, my goal is to walk through all of this, obviously in a little bit more detail, and tie it back to the existing literature. Thanks.
Thank you very much, Melody. So I just have 2 questions. So first of all, so here the asymptotic relative efficiency should be the higher the better, right? I think based on your explanation, you seem to think the higher the worse.
Oh yeah, I might have divided by the wrong quantity.
Okay.
Yeah,
because so, the smaller the variance, the bigger the efficiency.
Yeah, I should be divided. I think I flipped it. It's 1 over the ARE then. Yeah.
Okay. And the next question is that, so maybe you need to specify, I missed that, what's the definition of the block in here, in your talk?
Oh yeah. So basically the blocks are, you would group the units into, before you assign treatment at all, you would just look at which units are similar to each other based on these X's that you have access to. Mm-hmm. So like you might look at age and gender and like education levels, and then you would then assign treatment randomly within the block itself.
Got it. I see. So it's a block formed by other covariates.
Right. You're not blocking on Y itself. That would be cheating.
I see. Thank you very much, Melody. So Shindra, let's move on to our next presentation. Zach.
Okay. Can you hear me?
Yes.
Okay. So I'm going to talk about ecological inference. And next slide, please. And you can skip the outline, please. Thank you. So the classic problem that's used as an example of ecological inference is trying to estimate the probability of an individual voting given their race or demographic information. So in the United States, voter turnout and whether someone has voted is public information, and in a lot of places it is too, but who someone votes for is of course private, and a lot of the time people's individual demographic information is also private, although just like voter turnout in a given district, demographics averaged out over a census tract or a census block at the lowest possible level that's available is public information. And anyway, so you may have 2 sets of aggregated data, voter turnout in a region and demographic information in a region from the census, and you might want to estimate that probability that I mentioned of probability of voting given someone's demographics. So this is a 2-way table, and you are all, so if you click next slide, I think it'll animate a little bit. So there will be some, you only have access to those marginal quantities in red, and you want to estimate the quantities in the middle. So this is the classic example. And it turns out that just looking at the correlation between those marginal quantities over different regions, different aggregations, you can't necessarily derive the conditional or joint probabilities or parts of the distribution. And we'll see that more on that later. But first, I'm going to give a few more examples. Next slide, please. So just because the examples are kind of fun, So another example is if you had 2 elections and you know how many people voted for each party in both elections, you can't necessarily derive how many people voted for the same party in the 2 subsequent elections. It's unknown whether people switched in large part. Okay, you can go next slide. These are really fast, these next few. So you only have access to the marginal or aggregate quantities of how many people voted in the 2 elections, but not how many people voted in one election for one party and the next election for another. Another example that is from a recent submission that I had the opportunity to look at is about gene expression. So you may be a biologist and you may have access to tissue surveying tools where you can measure the amount of different genes or maybe even proteins in a given piece of tissue. And you might hypothesize that because 2 molecules often appear together in a tissue, that cells express them together and that they might be part of some cell metabolic pathway. And for the same reason that I'll mention and that I'm getting at, you can't necessarily infer that. So just from the tissue level measurements, you actually can't necessarily infer how whether 2 genes are expressed together in a cell level. You only have aggregate information. Okay, next slide. Fully next slide, please. Okay, so another related example that I think is fun, although it's not the main thing that gets talked about in this particular topic, is something called Simpson's paradox, which in particular happens when a correlation actually has the opposite sign of an aggregate correlation. Although in my paper, I'm going to articulate this in the language that is more commonly used for ecological inference, because this is a topic that I just kind of made a connection to. But in the 70s, UC Berkeley was sued because their acceptance rate for women was far lower than that of men. And then they surveyed their departments and they noted that every single department actually admitted women at as high or higher a rate than men. But the explanation for why women were being admitted at lower rates is because they were applying disproportionately to departments that have lower admissions rates. So more women were applying to English and humanities departments that are less funded. And so this is an animation that I made where you can sort of play with how many women apply to science departments, which have higher admissions rates. So even though women have higher admissions rates to both types of departments, if you click through these slides kind of quickly, I think there are like 10 or so, you'll notice that the number of men admitted actually surpasses the number of women admitted when just the ones with, yeah, okay, next one. So women get admitted at lower rates, even though their admission to individual departments is higher. Okay, next slides. Very quickly, I'll mention that trying to make inferences from those marginals that you can't actually make, or assuming that they imply the same relationship between the joint or conditional probabilities, is known as the ecological fallacy, and it comes up all the time. Next slide, please. I'm sorry, I thought I had 10 minutes. Okay, this is just notation noting the model. I think I just have a few more seconds, but you can flip through 2 slides and then I'll mention one way that people deal with this, if you don't mind. So next slide, please. Next slide. Next slide. Okay, so this is the most common way of dealing with this that was proposed in the 1960s or maybe even the 50s, which is that you'll notice that the 2 marginal quantities have an exact deterministic linear relationship. And so you can take all of your marginal quantities and do linear regression on them. And if in fact you have, anyway, and then when you estimate the slope and the y-intercept, you can then recover those joint probabilities. But it turns out that even though this is really popular and was really popular when it was invented, it looks very clever. It turns out that only under even some very specific conditions can this in fact extract an unbiased estimate of the joint probabilities or conditional probabilities, whichever you're interested in, or joint correlation, which are sort of all equivalent if your data are binary variables. Okay, that's all I'll say for now.
Thank you very much, Zach. This is a very interesting talk. It's just that you have many more slides than we could digest in such a short time. But the slides are very well made, especially the cartoon. That's very informative. So yeah, so I think to just as a one sentence summary for your part, I think the ecological fallacy is about the difference between aggregated data and individual data. And that would cause some interesting problems. And the Goodman regression is something good to know for all of us.
Yeah, even though it's not good to use it.
It has two strong assumptions, right? Okay. Okay, so
right.
Andy, yeah.
Okay, so I wanted to go over a simpler way of modeling species abundance in a diverse community. So you can see two diverse communities here. Next slide. So one way, so ecology is a study of understanding like mechanisms that dictate species abundance. And one of the more common distributions is the species abundance distribution, as shown on the right. So you can see here, I'm looking at powers of 2 on the x-axis, and it could either be number of species on the y-axis, as I have here, or it could be an actual like probability there. So you got more of a density function. So the number of modes matters a lot, because if you have one mode, then you're looking at a few species that are rare or common and a lot in between. If you have 2 modes, then sometimes it's more of a rare or common species distinction. So it's useful for conservationists to determine what constitutes rare or endangered, and you can analyze the number of common and rare species. So how do you make the model accurate, but also simple enough to make the data collection feasible? So next slide. So there's 2 different theories to obviously make it accurate. So one is the niche theory. So species are regulated by various environmental factors, and diversity is a function of environmental heterogeneity. So you're looking at weather, climate, terrain. That all matters in niche theory. You see here that I've got 4 different niches. But if I want to create an SAD here, then I got a stratified sample. And so I got to go to each of these places. I ended up doing that on various hiking trips, but it would take a while for me to stratify sample this. So next slide. All right, the other is a neutral theory. So it's a more simple model where you don't take into account these niches. It's only reproduction, immigration, and death rates. So that's independent of other species around it, introduced by Hubble in 2001. So again, it's independent of species size, shape, or environmental factor. You would think, hey, don't environmental factors matter? Well, in less biodiverse communities, yes. But an important result is that as biodiversity approaches infinity, the SAD, the species abundance distribution, using the niche and neutral theories become one of the same. So this result was shown by Chisholm and Piccola in 2010. Next slide. So we go over neutral theory asymptotics. Since neutral theory is simpler, the asymptotics are simpler. So suppose you have a meta community of JM individuals. Nu is when a population member dies, is the one replacing it from the same species or from a different species. And theta is the biodiversity number. So the more biodiversity you have, theta is higher. And it's calculated with this formula here. So the expected number of species with abundance n is shown below. This is from Chisholm and Pacala. What happens when you allow that biodiversity number to approach infinity? Next slide. So I have two components here labeled 1 and 2 on the top. JM is also approaching infinity. That's a number of animals total in the meta community. So Watson's lemma, it should actually be a same order than sign rather than an equal sign. Gamma of A plus B over gamma of B is same order as B to the A when B approaches infinity. So I can use that and portion 1. So you got gamma jm plus 1 over gamma jm plus 1 minus n. You can see is same order as jm plus 1 minus n to the nth power, which can reduce because you're looking at jm approaching infinity, jm to the n. You can do the same thing with the second portion, so eventually get at the gamma ratio to be same order as jm of 1 over 1 minus nu to the minus n. And when you take the entire component together, you get the ratio shown at the bottom, which simplifies to theta over n times 1 minus nu to the nth power. So that's the asymptotically equivalent thing of when you let the probability distribution of a species with n individuals as you let theta approach infinity. Next slide. All right, so now if we want to do
an interruption, your time is up, so let's quickly wrap up.
All right, with Nietzsche theory, if you have k Nietzsches, you can do the same kind of asymptotics, but because the k Nietzsches equals 1, taking into account the entire meta community, then doing Nietzsche theory for each of the or neutral theory for each of the Nietzsches results in the same thing. Next slide. So again, in a rainforest like this, I can now just sample from one area instead of all the corresponding Nietzsches. All right, that's it.
Thank you. Thank you. That's very interesting. So Andy, Shinjo, please go to slide 6. I want to point out one possible typo. I think in equation 2, I think in the limit, the power of j sub m, it should be negative n. Just by looking at the formula, that's what I think. So that's why it can be canceled with the jm to the power n in equation 1 when you multiply them together.
Which word?
I was saying the limit of equation 2 should be jm to the power n, not jm to the power negative n, not jm.
Jm to the power. Okay.
Yeah. Okay. Okay, so let's move on to our, thank you, Andy. Let's move on to our next speaker, Ashley.
Okay, I'll get started. So hi everyone, I'm Ashley. I actually unknowingly kind of did something similar to Melody's where we're talking about the role of asymptotic theory in experiments. Slightly different topic, but hopefully you'll be able to now have a really good idea of this from now hearing 2 talks about it. Next slide, please. So just a brief overview of what we're going to be covering in the next couple minutes. I just want to give a brief primer on what online controlled experiments are, as Melody kind of mentioned before, and then some of the challenges that are facing online controlled experiments, and why asymptotic theory is important for addressing those challenges. And then I'll propose one practical solution applying the delta method from a paper that was published at KDD a couple years ago. Next slide, please. So it's kind of trivial, but it's worth mentioning. So online controlled experiments are basically just controlled experiments in an online setting. So similar to other controlled experiments, you just subject you divide your users into a treatment or control group by random assignment. And then your measurements or interactions with your system are recorded over a period of time. So this is a very elementary statistics concept, but it's for very high impact. You might have heard it referred to as an A/B test if you did like an internship in tech or are kind of researching tech companies. So that's something that Melody had also brought up in her talk. An important reason why they use online controlled experiments is because we want to establish causality. So a lot of times different companies may roll out certain software features like user interface changes or even different algorithms, and they want to measure whether or not this has a positive impact on user behavior. So some examples of those metrics might be like click-through rate, revenue per user, and page load time, which is one that I'll kind of go through in the example. So the diagram on the right side of the page is just kind of illustrating the process of an online controlled experiment. Next slide, please. So some of the challenges in online controlled experiments, or rather actually the statistical analysis of the experiment, is sensitivity. So there are often a lot of, because it's like usually employed at a very large tech company, there are a lot of different experiments that may be running simultaneously. And so we often really want to detect very, very small changes in a per user metric, because if you multiply that small change by millions of users, it actually results in a very material change, like to something like product revenue. And then there's also the complexity of the metrics. So a lot of times people might think that the metrics might be just kind of averages, but sometimes what they're interested in are actually quantiles or percent changes, which are a little bit more difficult to compute the variance for. And there are also computational limitations, obviously, because we're dealing with very large N. And then there's sometimes this issue of independence. So while there is randomization in these online controlled experiments, there is the distinction between a randomization unit and an analysis unit. And that kind of variation between the level at which you analyze and the level at which you randomize can sometimes create dependence between your observations. Next slide, please. So where asymptotic theory kind of comes in, as I mentioned before, with A/B tests, you're usually using a very large N, so we can apply certain properties of the central limit theorem, and the average treatment effect is usually normally distributed. And each of the challenges that I mentioned before are kind of revolving around this idea of proper and scalable asymptotic variance estimation. So we need to better be able to capture those true effect sizes, but we also need to be able to calculate this even if the randomization unit and the analysis unit are not one and the same, in which case we might have some correlation between observations. And lastly, again, because of that issue with computational efficiency, we kind of prefer closed form analytical solutions as opposed to computational methods like Bootstrap, because Bootstrap isn't exactly something that's very easily parallelizable, and you can't really use it as a distributed algorithm, whereas closed form solutions can be easier implemented in those settings. Next slide, please. So just a really quick recap, and I won't go through too much of this, but I wanted to provide one example that I'll be covering in my survey paper about applying the delta method, which is something that we did a lot in the homework and we studied a lot in class, to constructing confidence intervals for quantile metrics. So again, this is all review from the course, but if you just look at the last equation on the bottom of the slide, that is the sample quantile at P. There's a slight difference in notation versus what we used in the course because I'm using the floor here, but very similar concept. Next slide, please. So even though we kind of worked with this quantile formula before, it's deceptively simple in the fact that in practice, right, we don't actually know the density function F, and we don't actually know what the CDF is, or the quantile. So current methods to kind of address this use kernel density estimation, but that obviously has a trade-off between bias and variance. And because the density function appears in the denominator, a small amount of bias there can actually lead to a large variation or a large discrepancy in the variance. Or they might use Bootstrap to estimate, but again, that is not computationally efficient. And the second challenge here is that the condition of IID may not exactly be met. So kind of what I mentioned before, but the randomization unit might differ from the analysis unit. And so we might randomize at the user level, but then we might analyze at the page view level. So there is correlation between each one of those observed page level metrics. So an example of that might be looking at page load time. Next slide, please. So we obviously need to adjust the variance calculation. I won't go through all the formulas here, but if you look at the top half of the page, that's kind of what the setting would be like to calculate the confidence interval for that quantile metric if we had that each xi was IID. But because, again, you might randomize at the user level, whereas the page view is actually what's recognized or recorded, you kind of get this clustering effect where you have several page views potentially for a given user. And because of that, we actually need to change the way that sigma or the variation is estimated. And so they go through the math in the paper, and I'll include this in my survey paper, but basically we need to kind of adjust so that we're calculating a variance that also takes into consideration the number of users and the number of page views for a given user, so the number of clusters. And so by that, you can kind of adjust the formula to get a lower and an upper rank to actually fetch your quantiles and then create your confidence interval. Next slide, please. So this is just a primer for the other topics that I'm going to cover in my survey paper. That application that I just talked about with the quantile is just one way of applying the delta method. But again, as I mentioned before, some other metrics that you might want to use for A/B testing are ratio metrics or percent changes, where the confidence intervals and variance estimation need to be adjusted accordingly. And there are also different types of randomization experiments, like cluster randomized experiments, which also can use the delta method to better estimate variance. And then lastly, I talk about an example for the delta method in data augmentation. So in longitudinal studies, there might be certain people that are not actually continuous throughout the data, but it's not actually missing at random. So you can apply the delta method to adjust the variance calculation there.
So Ashley, we should wrap up.
Yes, I'm done. That's it.
Thank you. Yeah, this is a very good review. Yeah, so looking forward to reading your report. Thank you.
Thank
so
you.
Next, Gabriel.
All right, how's it going, everybody? Thank you for the chance to talk to you today. So today I'll be talking about a topic called conformalized quantile regression for finite sample prediction guarantees. Next slide, please. So the premise of the two papers that I'm gonna cover in my sort of review paper for this final project is basically, are there alternatives to asymptotics as was covered in this class? And in particular for prediction. So the setup is that you're given a data set of pairs xi and yi. Xi is a predicted variable and yi is a response that you're trying to predict. And your data set is of size n. So we seek to predict the next unseen response, yn plus 1, using a distribution-free prediction interval, which takes in as input the xn plus 1th predicted variable, and which was built using the data set. So this interval is going to be a subset of the real line. And ideally, this interval is such that the probability that the next observation's response is in this prediction region is greater than or equal to 1 minus alpha. So the basic assumption is that your xi, yi pairs in your data set, union with the unseen observation, the order in which you observe them is exchangeable. So for example, they can be IID from the joint distribution of x and y. So the first paper by Romano and co-authors proposes to build this prediction region using quantile regression, which is basically, as many of us might know, an estimate of this quantile function. So instead of taking the marginal quantiles as was covered in class, we're taking quantiles of the response y, conditional on a covariate value. Next slide, please. So for this slide, I'm just going to quickly mention the second paper, which was the motivation for me looking into the first paper. Like Melody and like Ashley, it has to do with causal inference. So we're trying to get a prediction region for the difference of causal effects for individuals. Other than that, next slide, please. So for these simulations, my response is going to be random variable z, which is a difference of two other random variables, u and v. And so I want to get a prediction interval which has coverage 75%, as was discussed in the first slide. So to do this, one natural thing to do can be to consider the blue line here. So on the x-axis, we have covariate values x. And then the y-axis, the box plot, is the shape of the distribution which we're drawing from. So we see that for most values of x, we have a little bit of skewness toward higher values, in particular for, let's say, x is equal to 0. So we want to estimate this blue line. Next slide, please. And so the way I do this when I draw data in these simulations from the population with the distribution that I showed in the last slide is that I take different sample sizes, 150, 1250, and 2500. And for each of those sample sizes, I have multiple replicates. And so I build quantile regression estimates using random forests. And so this is what I would call an uncalibrated prediction region using these quantile regression forests. And so I'd look at their coverage. And so that's what I would have on the y-axis of these plots. And then after that, I would calibrate these prediction intervals using the method proposed by the Romano paper. And so on the numerator on the y-axis, I have the calibrated coverage. And so if this calibrated coverage for any given value of x, which we have on the x-axis, is better, this ratio should be bigger than 1. And so what we see for the different sample sizes, especially for the small sample sizes, is that calibration, conformalized calibration typically helps. So the takeaway of this paper, calibration for prediction intervals, especially with quantile regression, helps. So
thank you, Gabriel. This is very good to know. So basically, your numerical results is only about the first paper, the Romano paper, which is about the conformal quantile regression. It's not about the second paper about the causal effects.
Yeah, not yet. So in the write-up, I'll expand about that a little bit more.
Okay. And also, where is the conformalization? Where did the conformalization lie in? So my understanding is that it means, okay, your training data and your prediction data, test data do not belong to the same population. So where did that occur in these two papers?
In the Romano paper.
Mm-hmm.
So they estimate the quantile regression function using something like random forests.
Mm-hmm.
And so this would be I guess you would call it the unconformalized prediction region.
Okay.
This is quantile regression.
Mm-hmm.
So so that's with the training set, and then with the calibration set, separate from the training set, they put the predictions. They check how well the predictions were for the calibration set.
Mm-hmm.
And then they use a sort of quantile residuals, they define them as, to calibrate the new,
I see. So they have the training set, they have the calibration set, and then they have the test set.
Yes.
Okay, got it. Thank you, Gabriel. This is very good to know. Very nice presentation. Okay, so let's move on to our next speaker. And that will be Jia Liang. So Jia Liang, are you there? Yes, I think he or she is in the Zoom.
Hi guys.
Hello.
Hi. Yeah. Hi guys.
Okay, please start.
Yeah. Hi guys. I'm Jia Liang. So today I'm going to talk about the estimation of diversity index. Actually, it's estimation of linear diversity index. So yeah, but yeah, next slide, please. And next slide, please. So next slide. Yeah, that's this one. So what is a diversity index? So the diversity index is a function we use to estimate the diversity of the objects we want to study in nature. Sometimes it can be the diversity of the features in linguistics. Sometimes it can be a diversity of the cancer cells in a tumor. And before I give a definition of the diversity index, let me first introduce some preliminaries. The first one is the L set. The L set is the set to describe a population. So each LK represents a species in a population set, and it is a countable alphabet. So each LK will also have a probability which represents the abundance of this species, and the probability will form this P set. And the cardinality of L set is finite or countably infinite, because the L set is is a countable alphabet. So this 3 is important for defining the diversity index. And here we can get the diversity index, which is theta. Sorry, I don't show the detailed definition, but I will show some examples in the following slide. And the theta is called the diversity indices, and it has to satisfy the final 2 conditions. The first one is it is fully determined by P, which means it is determined only by the PK. And the second one, it is invariant under any permutation on the index set. So if we change the K to be K minus 1 and the K minus 1 to be K, and the theta function will still be the same. Next slide, please. Yeah. But usually the diversity index we study in nature are often the linear diversity index, which I will show you in the next slide. And it can be represented as a combination of a basis, which is the entropic basis. It is very similar to the vector space. We often use the generalized Simpson diversity index to define our entropic basis, which is the sum of pk times u and multiply 1 minus pk times v. We only pick a subfamily of it by setting the u to be 1, and then this eta 1 is our entropic basis. Next slide, please. Here are some examples of the linear diversity index, like the Simpson index, which is very straightforward because it can be directly rewritten as the linear combination of the entropic basis we have defined in the previous slide. But for some entropy or index, like the Shannon's entropy, we need to do some like the Taylor expansion and rewritten as the form we want. Next slide, please. So finally, to the topic, can we give a good estimation of this linear diversity index? Yeah, the answer is yes. And let me give a detailed definition for the theta again. The theta is called the linear diversity index if it can be written as this form, which is a linear combination of the pk times 1 minus pk times v. So this one is the sum of it is called the zeta 1v. It is the basis, and omega v is the coefficient. And we want to rewrite it as this form, the second equation, which is eta n plus.
So Jialiang, sorry for the interruption, but you only have 1 minute to go. So please quickly wrap up.
Yeah, sorry. I will go through it quickly. Yeah, so that the reason we want to do this is that usually we use the plugin estimator, but the plugin estimator is not an unbiased estimator for this problem, and the decay rate of the bias is 1 over n, which is not fast enough. Next slide, please. So we will use this the equation 10 as our estimator, and the bias can be controlled by an exponential function, which is defined at the 13th equation. Next slide, please. Next slide, please. So sorry, we don't have time today, so I'm just go to the conclusion. Last slide, please. Yeah, so we can use the Slutsky theorem to prove these following equations. The proof can be complicated, but let me see if I can show that on the report, because it is really complicated. So we want to focus on the last equation, which give us the way to estimate the estimator we get. It is asymptotically to the normal distribution. And next slide, please. Sorry, we don't have time today. So that's pretty much for today's presentation. Thank you.
So one quick comment, Jalian, before we move on to next talk is that, okay, so in your slides, I don't see any references. So I have no idea until I see the reference page where the results were.
I do have the references. Yeah,
okay.
This page.
I see. So still, I see most of the work was done in the statistics community. So my quick question is that is this estimation of diversity indices a question of interest in ecology or in at what field?
It can be widely used. Most of the time it's used in ecology, but sometimes it can be used in biostats like the cancer cells.
Oh, okay.
The type of cancer cells. Yeah.
Okay. Okay, thank you. This is a very interesting topic to learn about. Yeah.
Yeah, thank you.
Thank you. Okay, so Hedy is our next speaker.
Hello?
Hello. Yeah, we can hear you.
Can you see me?
Yes. We can see you and we can hear you. Okay.
Yeah, so today I'm going to talk about the double descent phenomenon, also called the deep double descent phenomenon because it's like mostly related with deep learning. Next slide, please. So the deep double descent phenomenon, in general, it's called double descent phenomenon, is saying about, so it's an interesting fact where, so as we are formulating a model, as the model size increase, we will start from a place where we are introducing a lot of bias since we have a very small model towards some optimal point. And then if we increase our model size, we will have the problem of overfitting. So that's what we call the classical regime. So what happens is that in practice, we see that as we increase the size of the model further, there's a second descent happening where the model starts to stop overfitting and start to perform better performance. And what happens is it has a almost perfect training error. So it does not, but it sometimes has training error because your data might perform different output for the same input because there's a random out there. However, it will perform extremely well still on the test data, despite the interpolation happening on the training data. And that's the phenomenon that happens. Next slide, please. So we will talk, for this talk, we will focus on the linear regression problem. That's the most well-studied one. And however, in the paper, we discuss about the other two papers that talks about the two-layer neural network one, and also the random feature model one. So linear regression one is the most well-studied one. Okay, so first of all, the phenomenon happens because, I mean, it doesn't happen from nowhere. It has to happen from somewhere, and that happens from the optimization method we use. And the optimization that contributes to this one is actually the gradient descent. Most recent algorithms to do optimization are improvements on gradient descent algorithm. So they should have a similar pattern, although they have difference. And theoretically, these theories about gradient descent may not apply. Still, it's going to be it still needs more study on that one. So for linear regression, let's start briefly about linear regression. You could always put the constant term inside. To some extent, you don't need to worry about that. You can write it in the matrix form, given if you have finitely many data. You may not have a solution in general because you have some error term. So you solve the minimization problem in the two norm in general. And when you have more data than attribute, you are in the traditional regime, you are stable. And otherwise, you are not stable and you are a tall matrix. And usually you use the QR solver for this one. The next slide, please. And what happens is in the underparameterized regime, the problem is convex. It has a unique solution. So whatever optimization method you use, you're always going to converge to that unique solution. And so the problem has fixed results, and it follows the statistical theories about machine learning. However, in the overparameterized regime, this says that if you start at 0, the gradient descent will always make the vector inside the span of X transpose. So you are always in the span of your data transpose. And what happens is you are going to get a solution that satisfies the formulation where you are minimizing the weights subject to y equals xw. So you are interpolating it and you're also minimizing the weights. This minimization problem, only happens when you start at 0 and you use gradient descent. Well, if you start at something close to 0 and you use something close to gradient descent, it may have some similar properties, but it might not converge at the point you want. But that's where early stopping comes in. If you stop earlier, you will get somewhere close to this minimization problem. So next slide, please. So what happens is this solution is actually called the Moore-Perot inverse solution theoretically. And if you want to solve for this solution, it's better to use singular variable decomposition or PCA inherently. And what happens is it's equivalent to solving the ridge regression, where the regression the regularization constant converges, like limits to 0.
So Hedy, your time is up. Let's quickly wrap up.
Sure. The next slide. Next slide, please. So it's like, so when we have the limiting behavior, we have the bias and variance converging. And yeah, and we have the statistical results about what happens when you have more data than your parameter. Yeah. So that's a limiting behavior. And that's a graph for that. And I think that's it. So if you want to look at the random feature models, the two-layer neural network ones, here are 2 links to it. And yeah, there'll be more details in the paper I wrote.
Okay, thank you very much. So basically the theoretical results for the over-parameterization is requiring that I saw that the number of features over the number of data points, the sample size, that ratio should converge to a constant as n goes to infinity.
It does not have to converge to a constant. But it has to be greater than 1. So in theoretical result, it has to, if it converges to a constant, we can analyze a constant. But if it does not converge, there is some variations in it, but there's a general bound of that.
I see. So basically that explains why you will have a minimum in the over parameterization case.
Yeah.
Okay. Thank you. So looking forward to your paper.
Thank you.
Thank you. Okay, our next speaker is Ian.
Yes, hello.
Hello, please start.
Okay, so I'm going to be talking about asymptotics in spatial statistics, actually a little more specific than that, but I'll explain in a bit. So next slide, please. So we're going to be focusing on a couple asymptotic properties of spatial data. And so when we're looking at spatial data, if you can think about this, either spatial or spatiotemporal, it's typically expected to have some sort of spatial correlation. So, you'd expect things closer to each other to be similar, right? And so we express this through something called a covariance function. And when we're talking about specifically certain types of spatial data, we call it a covariogram. We also can use a semi-covariogram. And these functions obviously have parameters, and they usually fit with maximum likelihood methods. And so it's helpful to look at the asymptotic properties of those estimators to try to see what's going on. Next slide, please. Okay, so I primarily focused on a paper that was explaining two sorts of asymptotic frameworks that are used in spatial statistics. So one of them is what you'd call increasing domain. And what that means is that the minimum distance between sampling points is bounded somewhere away from 0. Now, if you can imagine, as the number of points goes to infinity, that would mean you'd have to have a unbounded spatial domain, since if there's a minimum distance, then you put enough points, you have to go somewhere, right? The other type would be called infill asymptotics. And that would mean that points are taken more and more densely in a bounded domain, so you can't go anywhere. And from what I read, it seems like use one or the other depending on the problem you're sort of looking at. So if your problem lends itself to infill asymptotics, you might want to go there. And if it lends itself to increasing domain, you might want to look at that for analyzing your estimators. Next slide, please. Okay, so I'm going to specifically looking at Gaussian spatial processes. And it's, as you can imagine, a process where every single collection of variables is a multivariate normal design. And so we're going to be looking at some sort of results from both of these paradigms, so increasing domain and infill asymptotics. Next slide, please. Cool. So I'm going to be talking about some results from Marty and Marshall in 1984, and they're looking at this under the increasing domain framework. So I have a bunch of notation here, so you don't need to know all of it, but I like to write out a lot of my notation for our paper. So anyway, basically we have a Gaussian process represented by YT, and then capital T is an index set. And so it's some sort of spatial domain. It could be a lattice, it could be a set of spatial entities, it could be just, R2. And in this specific case we're talking about, we're assuming that the expected value of YT follows, is equal to XT times beta, where it's some sort of parameter vector. So we're actually assuming that we have regressors and a parameter vector in there. So in addition, we're going to be having a generic covariance function between 2 points, yt and ys, that will be recognized as sigma. Sorry, this is a typo. It should be ts and theta. And theta is just another parameter vector for the covariance function. And we're assuming this is going to be twice differentiable and positive definite. So obviously it's going to be represented as a matrix. And so just we're going to represent the covariance matrix as Vn, and then phi as the combined parameter vector. Next slide, please. I'm not saying phi right now. This is just a log likelihood. So as you can see, we just have a log likelihood of a multivariate normal, basically, just noting that we have x and beta as our expected value. Next slide, please. Cool. Again, there's a lot of specifics to this, but basically we end up looking at both beta and theta separately. And we have just representations for the first derivative and the second derivative. So the gradient and the Hessian. And then we have the information matrix with diagonal of B beta and B theta, which again is just notation. Next slide, please. Okay, so basically we want to ensure that our MLA estimates of theta n and beta n are both consistent and asymptotically normal. So not to get into all the details, but we need consistency, growth, and convergence of the information matrix. So to ensure our growth, we need that the limit of the inverses of B theta and B beta, which are kind of the diagonals of the information matrix, go to 0 as n goes to infinity. And then to get the convergence of ln2, which would confirm our consistency and asymptotic normality, we just basically, what's the word for it? Scale our Hessian matrix and confirm it converges in probability to the unit square. And to do that, again, we just confirm these values represented by A1 and A2, convergent probability to 0. And, sorry, to the identity in 0. Next slide, please. Cool. So in this case, we have quadratic mean implies convergence in probability. So we just actually prove, we end up actually just proving that it's converges in quadratic mean. And this can be proven. I left out the mathematical details just because it would take too long. And so this confirms that our parameter vector is normal with that distribution, normal with the inverse of the information matrix at its covariance. Next slide, please. So I don't have much time left, but just quickly, for infill asymptotics, I looked at a paper by Ying, and essentially the results are very similar, but you have to make a lot more assumptions, at least in this paper, about the way the covariance function is parameterized. And so we actually end up using a specific covariance function. If you notice in the last one, we used a generic one. Next slide, please. The important thing I want to say is actually on the next slide. Next slide, actually.
Yeah, so let's quickly wrap up, Ian.
Yeah, so anyway, so basically when you end up doing this, the important thing is that you end up getting that asymptotic distribution for the product. Sorry, I put commas, I should fix that. The product of the parameters, and then if you do it for the individual ones, you actually end up getting specific, not with the overall sample size, but with more specific sample sizes. So thank you.
And so Ian, so this is quite dense. Can you give us a take-home message? So what is the parameter or estimator is this about regarding the asymptotics? What is the parameter it tries to estimate?
Yeah, so for the first one, for the increasing domain, you're estimating a regression parameter, and then also it's actually generic enough to just say a parameter involving that is any parameter of the covariance function. The second one, for the infill asymptotics, you're parameterizing the parameters from the exponential covariance function as well as the, no, I think it's just that, yeah, the parameters from the exponential covariance function.
I see. So they're from two papers, one about the increasing domain, one about the infill domain. I see.
Yes.
Okay, thank you.
No problem.
Okay, so our next speaker is Zhengqi.
Hi everyone, can you hear me?
Yes.
Oh yeah, so I'm from the electrical and computer engineering department, and today I'm gonna briefly introduce sample efficiency in reinforcement learning using the large deviation theory. So next please. Yeah, so first let me briefly introduce what is reinforcement learning. So it is basically some agent interacting with some environment where the agent will make some actions based on the state of the environment, and the agent will receive some reward so that the environment will transition to the next state. It is pretty theoretical, but let me just give an example. Next, please. So in this Super Mario game, the picture, the left picture is a game. So that's a state, the state of the game. And the action is that you can control Super Mario to move left or right or jump. So that's the action. And the reward is that there's a score for the game. Like when Super Mario reaches some specific point, the score will be higher. So that's a reward. And next, please. So another example is in AlphaGo. So the state is the board. So that's a matrix. And the action is that you can place a chess on whichever empty spot on the board. So that's an action. And the reward is that if you win, you get a +1 reward. And if you lose, you will receive -1 reward. So that's a reward. So next, please. So in reinforcement learning, a more formal way of describing this is using Markov decision process, which is basically a Markov chain, but with actions. So next, please. So that suppose we are currently at state S0 and we take action A0, then we have some transition probability. We can go to some other states taking that action. So but in reinforcement learning, these probabilities are unknown. We need to estimate it. So a very natural way is to take samples. We take n IID samples from this probability, and we use the unbiased estimator to estimate the probability. So we care about the sample efficiency, like how many samples do we need to take in order to make the estimation error to be smaller than some epsilon. That's a problem in reinforcement learning. Next, please. So asymptotic theory says that if we have n IID samples, then root n of the sample mean converges to Gaussian. which we can see that the convergence rate is approximately 1 over root n. And there's actually some more precise inequalities in large deviation theorem. One of them is Hostings inequality, which says that the estimation error is bounded by some term t, which is in proportion of the scale of the xi, the scale of the sample, and in proportion of the root n. So that's the theory. And next, please. There's also another inequality that if we also know the variance of xi, then, for instance, inequality says that the estimation error is upper bounded by some term which is dominated by the variance of the sample. The next, please. So these two inequalities, we can use them to get the sample complexity. We just let the estimation error to be smaller than some epsilon. Then we can calculate n to be of the order of either the scale of the sample or the variance of the sample. So we get the sample complexity. That's a basic idea. So next one, please. But there's another very interesting setting in reinforcement learning that if we are given a feature map for the state and action pairs, that is, so we know that in Super Mario, the state is very high dimensional because each pixel is 1 dimension. But the feature, you can see the feature in the Super Mario is the position of Super Mario. So that's 2 dimensional. That is very much lower than the original state. So if we can utilize this feature, then it is much more efficient. So suppose that the transition, we suppose that the transition is linear to the feature vector. But you may think that this is very unpractical. How is it linear? But next one, please. But actually, in practice, this works very well in recommendation system. Like if you are browsing some news websites, then the website will recommend you with some related articles. That is utilizing this linear MDP algorithm. Also, they will recommend you some advertisements, which is pretty annoying, but actually that is also reinforcement learning. So the problem becomes we want to estimate the linear parameter theta. So next one, please. And next one. So a very natural idea is using least square estimation. We minimize the L2 norm of the error term, so we get the theta hat equals to some gram matrix inverse that thing. Yeah, so next one, please. So we still care about the sample complexity for this estimator. So we want the estimate error to be smaller than epsilon. Then how large of this, how many samples do we need to take? But this is not so easy to analysis. Next, please.
Sorry, we need to wrap up, Zhengqi.
Oh yeah, it's gonna be, yeah. Next one, please. So there's a theorem in recent years, and it shows that the sum of xi times yi is upper bounded by something. Next, please. And next, please. So I've got to skip these things, but the basic idea is that the estimation error can be upper bounded by some term. And next, please. So that we let the estimation error to be smaller than epsilon, then we get the sample efficiency, sample complexity. The last line is the D is the dimension of the vector and R is the variance of the label. So that is pretty elegant. So that's basic idea is a simplified model for sample complexity in reinforcement learning. Thank you.
Thank you. So thank you very much, Zhengqi. I just have one quick question. So regarding that theoretical result, so in the sample size, in the order of sample size, it seems that there's no term related to the Markov decision process itself.
Oh, yeah, I omitted a lot of details. It's actually much more complicated. It is in terms of state and action, but I just simplify to make a simplified mathematical model.
Okay.
That it doesn't have that term.
Okay, and there's one more thing I want to point out is that in one slide, you have that transition from state S0 to state S1. You have that probability to be estimated, right? And on the other hand, on the right-hand side, you say you use a sample average, but you have, when you see the indicator x equals lowercase s. So I don't know what that s corresponds to, because it's not corresponding to S0 or S2 on the left-hand side. So I have a question about that.
S can be S2 or S0. If you want to estimate the transition to state S2, then you calculate how many times it went to S2, and you get the proportion. That's
I understand that. Just I think you need to clear that notation.
Oh, yeah.
Yeah, okay.
Yeah.
Thank you. Thank you. Okay, so our next speaker, so Sierra, please start.
Hi, I'm Kira. Sorry, it's spelled weird, but yeah, I'm Kira Servants from the Political Science Department. And yeah, today I'm going to be talking about a paper by Buchanan et al. About generalizing experimental results. Next slide. So the background here is basically that, as I'm sure most people know, there's been a really big push in social science research lately to establish causal relationships. And so that has led to a really big increase in the use of randomized control trials, or RCTs. And so, of course, when you have randomization, you get unbiased estimates and you have very high internal validity, but there's a lot of concern about the external validity of these results, or basically how well they generalize beyond the very narrow confines of the experimental population. So specifically, there's a lot of concerns about the non-random selection into the experimental group. And so basically the researchers here are asking the question of how can we generalize the results of an RCT to make inferences at the population level, which is usually what we actually care about. Next slide, please. So the basic setup here is that we're looking at potential outcomes. So Y0 is the outcome under control, Y1 is the outcome under treatment, and the central estimate of interest in this paper is the potential average treatment, population average treatment effect. So that's just the average difference in those outcomes at the population level. So we're going to set things up basically with a random cohort of M individuals that's drawn from the population, and then our non-random sample of N participants that are selected for the RCT. Then we just use S as an indicator to indicate basically whether or not you were in the RCT or not. And of course, treatment within the RCT is randomly assigned, which is indicated by D. And then for all individuals M and N, we observe some p-dimensional vector of covariates X. Next slide, please. So we have to make some central assumptions to make any progress here. So a very common one in all causal inferences, SIFA, which is basically that there's no spillovers between units and that we have no variation in treatment. We also need to assume conditional ignorability of trial participation, which is basically just that the outcomes that we care about are independent of the participation status in the RCT, at least conditional on the set of covariates that we have. And then of course, the treatment is randomly assigned. Next slide. So typically in an RCT, as I'm sure everybody knows, you can just use a difference in means estimator to be an unbiased estimate of the average treatment effect. So in the first line that Tau had is literally just the difference in the average outcomes among the treated group minus the control. And then what we're doing, we move to equation 1 is we're able to move beyond just the narrow N group we have to the N plus M and sum over everything by using the S indicator, which will zero out for all of the individuals that we don't actually observe. So again, as I'm sure most people know, if the sample was actually randomly selected, it's very straightforward to show that this tau hat is consistent and asymptotically normal for the pate, but that's pretty much never the situation that we find ourselves in the real world. Next slide, please. So the solution in this paper is to turn to the IPW estimator, which basically models the probability of being in the RCT sample using logistic regression, and then assigns weights for each unit based on that probability. So the probability that the unit ends up in the RCT sample. So the inverse propensity weighted, or IPW estimator, is exactly the same as the one we had on the previous slide, except for now we're going to weight all units by their inverse propensity or probability of being in the RCT sample. So the basic intuition here is that if you had an individual who is very likely to be in an RCT, we're gonna downweight you. And if we get lucky and we get someone that based on their covariates, we think that they're pretty unlikely to be in an RCT, we're gonna upweight them. So it's just a way to kind of calibrate our estimate based on the selection into the RCT sample. Next slide. So the central result of this paper and the main contribution is showing that that IPW estimator is consistent for the pate and asymptotically normal. So how did they actually do this? The situation that you find yourself in is basically that the random variables that you have are independent, but not necessarily identically distributed. So a common way to handle this type of situation for asymptotics is to turn to M estimation, which we didn't actually learn in this class, but is derived from a lot of the stuff that we did learn and uses a lot of the same techniques. So basically, you start off with this equation, vector equation, where you specifically are choosing your size so that the following equation will equal 0, and your estimand will equal the estimands that you're after, mu1, in this case mu1, and mu0, which are the average potential outcomes in the population. Next slide. So since I don't really have time, I won't really talk about M estimation that much, but basically all you need to know is that it was originally developed by Huber. It pretty much always has this form with the psi functions equal to 0. Next slide. And following a bunch of math, again, using a lot of the techniques we learned, you Taylor expand, and you can show some nice asymptotic results. And you basically end up with the general form in equation 2, which is really nice. Just shows that if you can get something that fits that psi function, then you have this general result of the asymptotic behavior is multivariate normal with the following variance. So even if you've never seen this before, you're actually probably somewhat familiar with it. That variance in equation 2 is actually the sandwich estimator, with A being the bread and B being the meat, which is where the Huber-White standard errors and all that comes from. Next slide. So basically the proof is a very straightforward application of M estimation with, again, those psi equations. You solve for A and B. Next slide. And you get the following results straight from the M estimation in equation 3. And then for our purposes, since we care about the difference of mu1 and mu0, it's roughly the difference of those two psi functions. So you just apply the delta method and Slutsky's theorem using stuff we learned in this class, and you get equation 4 showing that the IPW estimator is asymptotically normal. And you can actually see probably pretty directly where that variance term is coming from in the normal. You can see that G here is going to be, the gradient of G should be something like 1 minus 1. So when you do the matrix math on sigma, the big covariance matrix, you'll end up with something that has the diagonals positive and then minus 2 times one of the corners. So yeah, that's basically it.
Thank you. Yeah, this is a very nice introduction to this method. Okay, so basically I think your talk and Melody's talk and Ashley's talk give us a very comprehensive introduction to those asymptotics in the randomized control experiments. Yeah, that's very nice. Okay, our next speaker is Dongyuan. So when the slide is open, you're ready to start. So since we have been talking for quite a long time, right, since 3:30, maybe we can take a short 5-minute break before we resume with Dongyuan's talk. I think everyone needs a break. Okay. Okay, Dongyuan, maybe let's start at 5:25. So let's wait for 1 more minute.
Okay.
Yeah. All right, so Dongyuan, let's continue. Welcome.
Thanks. Can you hear me?
Yes.
Hi, I'm Dongyuan. Today I'm going to talk about the test of multimodality. Next, please. And here's the introduction. So here we define the multimodality as we have the mode of continuous distribution of all of the local maximums, or we can just call it peaks. So here, for example, for k belongs to a positive integer, the testing problem or the number of mode is the null hypothesis is j equals c k, and versus alternative j is larger than k. And here are some distributions from my research projects, and we can see for the distribution 1 and 8, it looks like they are unimodal. But for the distribution 2 and 3, it looks like they at least have 2 peaks. So that's a problem we want to identify in this testing problem. Next, please. So here we briefly have we have two challenges. The first thing is we need to find the distribution-free test. So if we have some underlying assumption of the distribution, for example, a mixture of Gaussian, then we can just use a likelihood ratio test. But for more general cases, we need to have a distribution-free test because we don't know the distribution. And the second thing is that we need to have a non-parametric estimator of the density. So the kernel density estimator may be the most obvious choice, but it depends on the parameter. Next, please. So here's the kernel density estimator of function f is defined as following. So the most important parameter is called the bandwidth. So from the figure, we can see like if we have smaller bandwidth, then we'll have much higher number of peaks. But if we use a very large bandwidth, then we'll have only a few peaks. So that's a problem of using this kernel density estimator for the multimodality test. Next, please. So here we have two different approaches to test the multimodality problem. The first one is a critical bandwidth, and the intuition behind it is just how wide a peak is. And the second one is the excess mass. The intuition behind it is how high a peak is. Next, please. So if we are using the Gaussian kernel density estimation, then we can define the k critical bandwidth as just the smallest the smallest bandwidth which that your kernel density estimator has at most k modes. The very nice thing the author proved is that there's a relationship between the critical bandwidth and how many modes your kernel density estimator has. So you can see from here, we can actually see this function equals to the p-value. And we know if we want to test how many peaks we have, we just need to use the critical bandwidth. Next, please. So here is a figure. We can see if we use a smaller critical bandwidth, we will have a black dashed line, which has much more peaks. But if we use a larger critical bandwidth, we will have a solid gray line, which has smaller number of peaks. Next, please. So the intuition is that H0 will be rejected for large value of HK. So the question is how to get the distribution of HK. So the asymptotic distribution of HK is very difficult to find because we need to have a distribution-free test. But recall we have the relationship between the critical bandwidth and how many modes our kernel density estimate have. Therefore, we can construct the bootstrap data from the FHK hat. So we want to construct the B subsamples of samples of the bootstrap samples, and the author proposed a very nice idea. So it is just the rescaling of the original bootstrap samples by a factor. So this extra factor actually takes into account that if you use a kernel density estimator, you will increase the variation of the function. So divided by this scaling parameter will let your distribution closer to your real underlying distribution. And the p-value is just as usual in bootstrap method. Next, please. And the second method, the exercise mass, is a little bit hard to understand. And here, for a given constant lambda, we define the exercise mass as following. So if F has k modes, then we can divide it as at most k disjoint connected sets over the support of F. So we call this lambda clusters. And the exercise mass can be defined as following. Next, please. So I think the function is very difficult to understand, but if you can use this figure. So we can see here, given a specific lambda level, we have two lambda clusters, C1 and C2. And the excess mass is just a dark area. So it means that how much your density function exceeds this given lambda level. Next, please. And the empirical excess mass is just defined as following. So the basic idea is we can try to calculate the distance between k+1 excess mass versus k excess mass. And these differences can represent how much differences or how good k+1 mode describes your data compared to only use k modes. So the test statistic is defined as delta n k+1 as maximum of this difference of excess mass. And
so
the asymptotic distribution.
Let's wrap up. Yeah, your
okay.
time is up.
Yeah. So this asymptotic distribution is very hard to find, but we can still use the bootstrap. And next figure, please. So, sorry. Yeah, that's all. Thanks. And
okay, thank you. And Dongyan, I think this is very interesting, a very interesting topic. And I just have a question regarding the notation for the p-value for Silverman's method. You have that HK star. What is the definition of that? I think you use that for bootstrap, but you also have used that before defining bootstrap.
Yeah, I guess I should use like HKB star in the bootstrap cases.
And so what is the before one? So maybe Xinzhou, you can go to last slide, slide 6 of slide 5. Yeah, here in slide 5, the bottom, you have HK star defined there. What's that?
I think here HK is observed data you have, and maybe HK star should be think as a random variable. But I think maybe using HK star here is not very accurate.
Right, because HK itself is random.
Yeah. But here, actually, I think they also define HK as the observed statistic. So I may need to refine this.
Okay, yeah, I just want to point this out for you to check. Okay, thank you, Dongyan.
Thanks.
Okay, our next speaker is Shuang Mu.
Yeah, I'm here.
Okay. Okay, so Shuang Mu, please go ahead.
Okay. Hello, everyone. I'm Shuang Mu Pen, and I'm a second-year computer science master student. Today, I will introduce my survey topic for the final paper. This survey have two main reference papers, which are Xiaoli Meng's Statistical Paradises and Paradoxes in Big Data, and Water Dempsey's Paradoxes arising out of reported coronavirus case counts. I don't think I can explain the models and details in 6 minutes, so I will focus on only the general points. And for the background, although I think everyone knows what COVID is, but here's some like more detailed information. The WHO has declared the coronavirus disease, COVID-19, a public health emergency in January this year. By yesterday, there have been like 15 million case counts, about 0.3 million deaths, and 9 million recoveries in United States. Yet the data landscape for understanding COVID-19 remains limited. Public databases maintained by Johns Hopkins University and the New York Times provide incoming county-level information of confirmed cases and deaths. Statisticians, epidemiologists, economists, and data scientists have used this granular data to forecast COVID-19 case counts, deaths, and hospitalizations. And next slide, please. Oh, yeah. And for the motivation, the paper paradoxes arising out of reported coronavirus case counts expresses reservations at the use of this case counts as a proxy for disease prevalence and intensity, as well as its use as direct input into estimation of standard epidemiological models for inference and forecasting. The paper Statistical Paradises and Paradoxes in Big Data addresses in depth about the question on the potential limitation of big data. For example, like a sample question is, which one should we trust more? 1% survey with 60% response rate, or non-probabilistic data set covering 80% of the population. And I think Charlie Meng's try to focus on here is sometimes the data quality is it matters more than data quantity, and in our case, there have been like limitations in this big data, such as like imperfect testings. Some testings are given like to only patients with severe symptoms, and those who with little or no symptoms are omitted. And next slide, please. Oh, yeah. That just the previous slide, please. Okay, here's the plan of my survey. In the analysis of limitation of case count data, the paper paradoxes arising out of reported coronavirus case counts relies heavily on ideas from statistical paradises and paradoxes in big data. Charlie Meng's paper, for example, like in the estimation of the error between the proportion of positive tests in like N tests and the true proportion in the proportion of like positive patients in the population, the Walter Dempsey used the ideas like the product of data quality, data quantity, and the problem difficulty in his estimation. And for the survey, I plan to use statistical paradises and paradoxes in big data as theoretical framework, and the paradoxes arising out of reported coronavirus case counts as one application of the theory. Next slide, please. And finally, the relevance to the course. This survey will explore the limitation of large samples, which only assume a large sample size but cannot guarantee the independently and identically distributed condition. And next slide, please. I think that's it. Thank you for listening.
Thank you for the introduction. Yeah, I agree that Charlie Meng's paper is very interesting and very fun to read. He actually gave a talk about this in the, I think, the Joint Statistics and Biostatistics seminar maybe a year ago. So yeah, so this is something very interesting to check out for our students. Yeah, thank you for the introduction, Shamu.
Thank you.
Okay, our next speaker is Aditya.
Hi. Before I start, a disclaimer, I have swollen lips like Kim Kardashian or Kylie Jenner, so my pronunciations may not be clear.
So yeah, thank you for doing that, Aditya. It's not convenient, I understand. Yeah.
Okay, yeah. So I'll be talking about the estimation of information theoretic quantities. And I think this talk will be very close to the talk on diversity indices, which was done before this. So next slide, please. Yeah. So what is Shannon's entropy? Shannon's entropy is the measure of the amount of randomness of a particular random variable. So for a discrete random variable on finite alphabet, it's given by the green box, which is basically the expectation of a negative log probability of a random variable, which is nothing but the number of bits required to encode the random variable. And this entropy has nice properties, like the entropy of randomness is 0 when x is a constant, that is when it is not random, and the entropy is maximum when it's uniform, so it can take all the values at random. Next slide, please. Yeah. Similar to the entropy, you can also define a mutual information, which is a property of two random variables, and it measures the amount of information one random variable contains about the other. So basically, mathematically, it's equal to the expected ratio of the log joint distribution to the product of the marginals. So the mutual information between two random variables is 0 only when the two of them are independent. And when they have a 1-to-1 relation, it's equal to the entropy and it's the maximum. Now just note that MI does not make any assumption on the distribution of the data. So it's not like linear, non-linear. It can be general and can be applied to anything. Next slide, please. The question is, why do we care about this? Now we care because it captures general association between two random variables, which can be beyond linear correlation, and thus it can be used for testing independence of random variables. Also, in terms of modern day machine learning, it has been shown to be very useful for generalization of models, and it's also useful in learning effective representation of data like text-speech information bottleneck. However, mutual information is not bounded above, so it's a bit of a problem for us. Next slide, please. So what we can do is we can standardize the mutual information using the following relation so that it's bounded between 0 and 1. So what we do is that we have the following relation based on the definition of I and H, and then we can take A and we can divide this by any of the BIs, and you get an estimator which is bounded between 0 and 1, which is 0 when they are independent and which is 1 when they have a 1-to-1 correspondence between them. So basically we have an estimator which can be used for testing dependence of random variables. Next slide, please. Now, ideally, we don't have the whole population, but we have just a few samples. So we can estimate the joint distribution by using the relative frequencies obtained from the data, and we can call them to be p-hats. So it's like a joint distribution and the marginals. And what we do is we just vectorize them and form a vector v. And we can show using central limit theorem that this vector v obeys a Gaussian distribution asymptotically. And this will be useful for results on entropy and the mutual information. So can you go to the next slide, please? Yeah. So based on the empirical distribution which we obtain from the data, we can simply plug it in the entropy distribution, and we can obtain an estimator of the entropy for a particular random variable. And then using delta method, we can just trivially compute the Jacobian, which is the derivative of p log p, and we can show that the entropy estimator is actually asymptotically normal, and it converges to the true entropy in infinite limit. And here sigma h is like the covariance for the entropy estimator, which can be calculated using the delta method. Next slide, please. Yeah. Now the mutual information is a function of the entropy, and the pre-multiplying vector is just a 1, 1, minus 1. So we can again repeat the same procedure of delta method and apply it like 2 times to show that the mutual information we get is also asymptotically normal. And since mutual information is a single scalar, it's just a 1D random variable with sigma square as the variance. However, we know that the mutual information may not be bounded above. Next slide, please. So again, like since we've done this on the previous 2 slides, we can repeat the same argument, and we can compute the asymptotic distribution of the standardized version of the mutual information. Now I have done it only for one of them, but you can use any of the 5 terms and derive the exact same result for all these. Then we can use Slutsky's theorem, and we can replace the variance by the sample variance, and then we can use that as test statistics for performing hypothesis testing to check dependence of random variables if you want. Or we can also use it to check if the amount of information between the random variables changes with time or not. Next slide, please. Now, unfortunately, the paper I was reviewing didn't have any pretty figures, so I just ran a few experiments on Python. So what I do is I take x to be uniformly distributed and y to be like absolute sin x, and I compute the Pearson correlation coefficient and all the 5 estimators we have. And we can see here that the data is nonlinear, and the rho is very close to 0, but the MI estimators are good, and they're like more than 0.8, and the highest one is equal to 1. So it means that these estimators work well on nonlinear data. Next slide, please. Similarly, you can do the same analysis for cos. Now, since the initial part is downwards, the rho is negative, but it's again poor, and the other estimators are really good. Next slide, please. And you can repeat the same thing for a cubic distribution. Now, since this is close to a linear distribution, rho is actually high and good. It actually beats a few of the MI estimators, but K1 is still the best, and it shows that the data is dependent completely, and we also captured that perfectly. So I think to summarize the talk, I would say that the information estimators are more general. They do not depend on the distribution of data or the relation between X and Y, and it performs well in both nonlinear and linear settings. And MI has also been used in machine learning, so it's useful in that sense as well. But unfortunately, these two papers only deal with discrete random variables. It could be interesting to see how they work for continuous random variables. And however, these estimators are plug-in estimators, so they have a high bias, but the authors have also proposed other methods to reduce the bias when you are not asymptotic. Next slide, please. Yeah, I think it's done. Thank you. Any questions?
So thank you, Aditya. Yeah, very interesting. So basically, for each of those mutual information definition or variants, you have a plug-in estimator. And
yes.
Here what you did is that you use numerical experiments to verify the performance of each.
Yes, how the estimators perform, yeah.
Okay. Was there any comparison before for those measures?
What do you mean before? I mean, in the paper?
Before, because you did the numerical experiments, but
no,
I mean...
The paper didn't compare with rho, but they had a few experiments where they just compared the values, but it's not pretty, so I didn't put it.
Okay, yeah. I see. Thank you.
Thank you.
Okay, our next speaker is Kang Cheng. Please start.
I will talk about the asymptotic frequentist property of the Bayesian inference. Next slide, please. First, let's have a brief recap of the Bayesian inference. With IID data, NIID data, we combine the likelihood and also the prior belief about the parameter. One can obtain the posterior and also have some kind of summary about the posterior, like either with a point estimate, theta hat, or the credible interval, like with some level. Next slide, please. Although like this is not a very Bayesian practice, because in a Bayesian setting, the theta itself is just a random property. It does not make sense to say about the true parameter theta 0. But however, one can ask the frequentist properties of the Bayesian inference. Assuming the existence of some kind of true parameter theta 0, one can ask about the consistency of the posterior, like whether the posterior concentrates on the true parameter theta 0 and also the asymptotic distribution of the posterior. And from a more practical perspective, the asymptotics of the variational approximation of the Q theta, inferred with variational inference techniques. Next slide, please. So first, we have a theorem about the consistency of the posterior. Under regular condition, for every true parameter theta 0 as n goes to infinity, the posterior will put all its mass on the true parameter in probability. This is the definition, if and only pi theta is larger than 0 for every theta. This is relatively simple, but it's saying when the pi is not too strong, the posterior will put all its mass to true parameter theta 0 in probability. Next slide, please. And then we discuss the asymptotic distribution of the posterior. The famous Bernstein-von Mises theorem states that under regularity condition, the posterior has asymptotic normality. Operationally, what you would do to understand intuitively about this theorem is that you sample n data points from the true model and you obtain the posterior with some kind of prior that satisfies the regularity condition, and which is the posterior. And you also construct another distribution of centered on the maximum likelihood estimate, and also the variance is obtained with some calculation with the Fisher information matrix. And you calculate the total variation distance between the two. You can show that the total variation distance converge in probability to 0 as n goes to infinity. An immediate implication on the practical side is that the Bayesian credible interval and the Wald interval are asymptotically the same. That being said, the prior does not matter in the large sample settings. Next slide, please. then we discuss the variational approximation of the Q theta of the true posterior. So first we provide some background of the variational inference. For most interesting models, the normalizing constant in the posterior is computationally intractable. Therefore, we need some kind of computational method to approximate the posterior. The variational inference transform this into an optimization problem, which is try to find Q theta within some variational family Q that optimize the KL distance between the approximated distribution and also the true posterior. One can show that it has some very nice properties. And why we use the family of distribution is the mean field family distribution, where like each dimension of the posterior factorizes. This assumption has shown to be like to achieve a good empirical performance for a wide range of interesting models, but it will be attractive to have some kind of theory behind it. Next slide, please. And in a recent paper, they proposed a variational extension of the Bernstein-von Mises theorem. It's saying that the VB posterior also have asymptotic normality. Operationally, what you will do is sample n data points, and you obtain the best variational distribution in the mean field family. And for the second distribution, it's some kind of model-dependent normal distribution. And you can show that the total variation distance converging probably to 0 as n goes to infinity. Next slide, please. To build more intuition about this theorem, recall that the variational inference posits like finding the posterior as an optimization problem. So you're starting from the Q initial and to the Q star, and which minimize the KL distance between the Q and also the true posterior. The reason that variational Bernstein-von Mises theorem holds is that asymptotically, the true posterior contracts to a point mass, which is factorizable, and it sits in the mean field family we are using. Therefore, the theorem holds. And next slide, please. Okay, so finally, we give the conclusion. We first show the consistency of the posterior, and we also show the asymptotic normality distribution of the true posterior. Finally, we show the asymptotic normality distribution of the variational approximation. And these are two like key references.
Thank you, Kangcheng. This is a very nice introduction, very clear. Yeah, and you know, this second paper's first author, Yixing Wang, she was a job candidate in our department last year.
Yeah, I went to that.
Yeah, so I just have one quick question before we move on. So in the variational Bayes theorem, so what are actually the two numbers in that normal distribution? So I know there must be some statistics, but what form do they take?
So I think they're like model dependent, but it's analogous to the MLE and also the Fisher information. And for different model, like it can take different forms, I think.
I see. But do you think it's general? Do they cover general distributions?
I think they prove like theorem for the mean field family.
Oh. No, but that's for the Q, right? I mean, for original data distribution, does that apply to a lot of?
Yeah, I think they hold for a wide family of distribution. Like they have like a lot of the applications.
Okay, thank you. Yeah, this is a very nice talk.
Thank you very much.
Okay, let's move on to our next speaker. So Deb.
Yes, is my voice audible?
Yeah, I can hear you. Okay, please go ahead.
Hello everyone. So I'll be talking about the quotient correlation coefficient and its application to testing the hypothesis of independence. Next slide, please. So testing independence is a very important research area in statistics, and various tests based on different correlation coefficients have been developed. However, the Fisher's Z-transformation test, which uses the Pearson's correlation coefficient, is highly efficient. However, it is efficient when the alternatives are linear dependence, and this test has poor performance when there are some non-linear dependencies in the data. And in this survey, we study the quotient correlation and look at its effectiveness in detecting non-linear dependencies in random variables X and Y. Next slide, please. So in this slide, we define the quotient correlation coefficient. So if we have two random variables X and Y, which satisfies some properties like they're identically distributed and have support in 0 and infinity, and the events X greater than Y and Y greater than X have non-zero probability, then we define the quotient correlation by the terms shown in the box. And by defining it in that way, it satisfies some interesting properties. The first one is that the quotient correlation lies in 0 and 1. And the second and the most important property is that when X and Y are independent, the quotient correlation tends to 0. And this is because the term shown in red, when X and Y are independent, the term tends to infinity, as well as similarly, the term in blue also tends to infinity. And because there's a product in the denominator, we have Qn tending to 0. On the other hand, when X and Y are dependent, Qn is closer to 1. So Qn can be used as a measure to predict the dependence or independence between random variables X and Y. Next slide, please. So, so we are interested in testing the hypothesis, the null hypothesis that X and Y are independent versus the alternate that X and Y are dependent. So the main theorem of the paper is that under the assumption of some marginals of X and Y, the quotient correlation under the null hypothesis converges in law to a gamma 2-1 distribution. So based on this asymptotic distribution of the quotient correlation, a very simple testing procedure can be defined, which is called the gamma test. And the test is as follows. So we compute the value of NQN and then compare it with the upper alpha percentile of the gamma 2-1 distribution. And then we reject at 0 if NQN is greater than zeta alpha. Next slide, please. So this is a simple illustrative example where we show that the gamma test is much more efficient than the Fisher's Z-transformation test when there are dependencies which are nonlinear. So here we plot the power of the test, which is the probability of rejecting the null hypothesis. And we see that for this situation, the power of the gamma test tends to 1. However, the Fisher's Z-transformation test has poor performance in this case. Next slide, please. So we now arrive at this particular position where we know that when the alternatives are linear dependence, the Pearson's correlation coefficient is highly efficient in detecting them. However, it turns out that the quotient correlation is worse compared to Pearson's correlation when the alternatives are linear dependence. However, the situation is reversed for the case of nonlinear dependence. And the natural question which we would like to ask is, can these measures be combined to get a better efficient correlation coefficient which is effective in both the situations? And the affirmative answer is yes, and it depends on a very interesting property of the relation between these two correlation coefficients, which we present next. Next slide, please. And the interesting property is that under the null hypothesis of independence, when X and Y are independent, the quotient correlation and the Pearson correlation of X and Y are indeed independent, which means that these two correlation coefficients are measuring two different aspects of dependencies between the random variables X and Y. And hence, if we combine them, we could get a more efficient test irrespective of the alternative hypothesis. And we define this combined measure as the max of the square root of the quotient correlation and the absolute value of the Pearson's correlation. Next slide, please. And now we again derive a testing procedure based on this combined measure, where in this case, it turns out that in the case of under the assumption of the null hypothesis, the combined measure has a max of 2 chi-square random variable distribution. And the testing procedure is just comparing NCN square with the upper alpha percentile of this max distribution. And we reject at 0 if the value is greater than the upper alpha percentile. Next slide, please. So finally, we do a comparison between the 3 tests that we just defined, the gamma test, the Fisher's Z-transformation test, and the max chi-square test. So on the left plot, we have a situation where there is linear dependence, and we see that the gamma test is has a very low detecting power, and the Fisher's Z transformation test has a very high detecting power, and the max chi-square test is very close to the to the Fisher's Z transformation test in this case. On the figure in the right, it is a situation where we have nonlinear dependence, and we see that the Fisher's Z transformation test has very low detecting power. The gamma test has very high detecting power, and the max chi-square test is very close to the gamma test in this situation. So finally, we can conclude that this combined measure, because we're combining two correlation coefficients which are asymptotically independent, we're able to leverage the power of both of them, and hence we get a test which is which has high like good performance irrespective of what the alternative hypothesis is. Next slide, please. These are some of the references, and are there any questions?
Thank you. Thank you very much, Deb. Yeah, as I said in my previous email to you regarding the report, I would suggest that you compare or just cite some references that compare this quotient coefficient with some other measures for measuring monotone but nonlinear relationships, such as the Spearman-1 correlation and Kendall's tau. And also, I know since this is something I have worked on, so I know a little about it. So there is a test called HHG test, which the authors have proved theoretically that this is the most powerful test. So probably I'm very interested in how this combined measure you mentioned sits in the literature compared to all the other measures for capturing the dependence between two variables.
Okay,
yeah.
I'll do a look at this.
And also there is maximal correlation and distance correlation. So these two things are supposed to capture any dependence between two variables. Yeah, so there are a lot of things out there. I'm just very interested in where does this combined measure sit in?
Yeah, I do have some papers which compare it to Spearman's, but I'll include them in the report as well as I look at these correlation measures.
Yeah, thank you. Yeah, thank you very much.
Thank you so much.
Okay, so our next speaker is De Qian, if that's the correct pronunciation, or Brian.
Right, it's correct. Hi, I'm De Qian Kong. Today, my topic is to look into the asymptotic behavior of the neural network. Next slide, please. Literally, most of the theory of deep learning guys only care about the growth function and VC dimensions, but asymptotic behavior. That is actually a leftover question for me before. Recently, I finally found I was able to figure out some of them. So that's why I chose this topic. First, I want to give a basic knowledge of one layer neural network. Here by one layer, I mean one hidden layer. So given a set of data X, fitting a neural network with one hidden layer is just a parametric nonlinear regression problem. It's parametric model because we have already known the number of hidden units, right? And I also have drawn a simple visualization of one layer neural network here. Okay, so next slide, please. You might have heard of the universal approximation theorem before. Here we use a Stefanko version, which is around 30 years ago. He said that given a continuous activity function, we can use a summation of this form, just like the neural network form, to approximate any continuous function. To be fair, a recently flourishing deep learning model is mainly related to convolutional neural network, recurrent neural network, and we also have a new version of this theorem. However, today, I only focus on the one hidden layer neural net. Next slide, please. As for asymptotic behavior, it's mainly about the existence, consistency, and asymptotically distribution. Here we have a formal definition of our estimator that is given input observations as X. We assume the true model as F0 and the response Y comes from the true model plus randomness. Then we can get our estimator by minimize the population mean square error, right? Here we have two kinds of settings. The first one is parametric model, which is just we use everything, we use mostly in our daily life. The second one is non-parametric model. At this term, we do not know the number of hidden units, so we need to determine this in its function space, just as calligraphy F, right here. Okay, next slide, please. As for parametric model, I have done a simulation study here. The data generating process is given by this. We have given observations X, and the randomness comes from epsilon. And the model, the response Y comes from the true model plus randomness. So it's a toy model here. What I want to is to try to train a one layer neural net with two hidden units to fit the data from this process. Next slide, please. So after around 30,000 iterations, I got the estimated F hat. So from this chart, we can see basically it's a lot different from the true model. So I also gave a plot of these two models in next slide. Next slide, please. At this time, we have exactly 0 training error, which means that this model has done its best to fit the data, but still cannot get the true model even in this extreme simple case. So basically, parametric model is an inconsistent estimator, right? Next slide, please. Next, I wanted to focus on non-parametric model. So it's a little bit complex here. The problem is that if the class of functions is too rich, it becomes intractable for us. So in this way, we want to construct a sequence of simpler function space to approximate the real function space, and this approximation error is 0 as n goes to infinity. So we can such a sequence of function space is called sieve. So we call it a sieve estimator. In one layer neural network setting, we know the function space is determined by the number of hidden units R. So we actually construct a sequence of function space, based on this. Here is the formal definition of our approximated function space. Okay, so next slide, please. Now we define the sieve estimator as before, but the function space is our approximated function space. As we know, as n goes to infinity, this approximated function space is close to the real function space. So here I also give the theorem of asymptotic normality, and I just give all the proofs, and I will give a sketch in the final paper because in its original paper it's about 45 pages to prove this. Okay, next slide, please. Next, I reproduced the simulation study as parametric model did before. We have exactly the same data generating process as parametric method. From this figure, we can see that as sample size increases, we indeed have the estimated model is more like the true model.
So the
just like this yellow. Oh, right.
Yeah.
Which means it's consistent. Next slide, please. Then we plot the residual. From the normal QQ plot, it's basically normal, right? Next slide. So in conclusion, I use several plots to give intuitive feelings that a parametric model of neural network is inconsistent, and a sieve estimator of the neural network is consistent and asymptotically normal. Okay, that's it.
Thank you. Yeah, this is very interesting. So basically, show that if the true function is a one layer neural network, if that's the truth, then if you use a parametric model, you cannot get a consistent estimator. But the non-parametric sieve estimator can do a good job.
Right.
Okay. Thank you. Yeah, this is very interesting.
Thank you.
Okay, this is our second. So Deqian was our second last speaker, and our last speaker today is Sixuan. Okay, please start.
Hi everyone. I want to talk about the asymptotic normality of MRE from multi-parameter response-driven designs. Next, please. Next, please. The responsive-driven designs for the arbitrarily assigned points to subjects It's very practical in many domains. First, we're gonna look at the some regularity conditions on the likelihood. Then, based on that, we're gonna look at the main theorem. After that, we're gonna focus on the 3 novel designs, and we want to make sure the conditions satisfied for the MLE exist from the stochastic process, and make sure the MLE are asymptotically multivariate normal. Next, please. And these are the regularity conditions. They're collected from a few books, are not very new. So we can see the conditions A1 and A2 are standard differentiability conditions. A3 and A4 assume the martingale central limit theorem. And A5 is a proof for weak consistency. And A6 is very important for consistency and asymptotic normality. Next, please. With the weak laws for martingale and the standard martingale arguments, we have the substitute regularity conditions. They're also very useful. It's not hard to figure out that A5 prime implies the A5 in the last slide, and the A6 double prime implies A6 in this condition in this slide, and A4 and A6 prime can imply the A6 double prime. And when the partial derivatives are bounded in each eye, then the conditions A4, A5 prime, A6 prime, and A6 double prime are very trivial to verify. So makes our proof to the consistency and the asymptotic normality relatively simple. Next slide, please. And the theorem developed by the Willem are if the conditions present in the slide, in the last 2 slides are satisfied, then we have the conclusion that the MLE exists and is asymptotically multivariate normal with 0 mean and the various covariance metrics like this. We're gonna skip the proof here. It's not out of our interest. Next, please. Then we're gonna talk about the 3 novel designs. One is generalized polyurn design. And this is kind of like the procedure of the design. Next, please. Because of the limited amount of time, I skipped some definitions and the notation here. So the likelihood gonna look like this. The Tn, t to the power n, x to the power n, and y to the power n are the history of response over assigned treatment and of the composition up to the stage n-1. It looks basically like this. Next slide, please. We assume the initial composition being fixed, so we can have the sigma algebra generated by the stochastic process through stage n proportional to this, and then we derive. We do the derivative, and we have things on the second line, and then we do the MLE for the PJ hat, and we have the result in the third line, and it's basically as the proportion of observed the response of treatment J. And now we focus on the proofment of the proofment of the consistency and the multivariate normality. So we try to focus on the regularity conditions we presented before. And A1, A2 are very trivial to verify, and A3 needs more attention. Then there are two conditions. One is J not equal to K. The treatment is not equal to the K does level.
So just for the information, you only have 1 minute left. Let's quickly wrap up.
Okay, sure. And for J not equal to K, the non-random function of theta is gonna be 0. If it's if it's equal to K, then we have things. It's not presented here, sorry. So I'm gonna like just conclude that without the improvement, we have the resulting limit law of MIE vectors is asymptotic multivariate normal with mean 0 and the matrix with off diagonal elements 0. And next slide, please. And the up and down design is basically the same with different notations. Next, please. And the likelihood for the model is almost the same and like as the previous design, and that the PJ is consistent with the erratic Markov chain result. So we have the almost the sure consistent and the consistency property.
Yes, we have to stop. Your time is up.
Okay, sorry.
Maybe use 10 seconds to say what's remaining.
Yeah, can I have 1 minute to like wrap up?
I'm afraid that that's not fair for our class because I didn't give them that time. But so I can give you 10 seconds to wrap up.
All in all, the 3 innovative experiment designs involved like developing the MLE for multi-parameter responsive driven designs. And with the proposed regularity conditions, we basically try to prove the MLE of each design is asymptotic and multivariable normal. That's it.
So here the asymptotics, I think what you showed are the consistency, right? Are all the results about consistency, or you also have the asymptotic distributions of those MLEs? Because if they're MLEs, then yeah, definitely they have the asymptotic distribution when the regularity conditions are satisfied.
Yeah.
Okay, thank you. Is this related to your research?
Not really. Not quite much.
Okay, I see. So how did you choose this topic, the response-driven design? It's actually quite interesting.
Yeah. I think I'm more into the stuff in application. So I read this article, this research paper, and that is about the designs and the studies in this practical. It's very like useful in application. So I love this part.
Okay, great. So I look forward to reading your report. So yeah, that's all for today's presentations. Thank you all for your wonderful talks. And as an announcement for your report, which will be due next Friday, I will suggest that because I realize many of you write your paper based on other people's survey papers. So my suggestion is that try to make your report incorporate information at least from 2 papers. So do not write based on just 1 paper. But you can have 1 paper as the majority of your content and the other paper as a supplement. That's okay. But please try to do some summary yourself. So that's my suggestion. And so also for the course evaluation, please don't forget that I think the university has extended the deadline because of some technical issues. So your evaluation will be extremely valuable and appreciated by me. So thank you for doing that. And so that's all for the talks today. If any of you have any questions for any of the speakers, please raise your hand or ask the question right now. I think this is a good time before we conclude. Otherwise, please feel free to leave because officially our presentation is over. So thank you, everyone. Any questions before we conclude? Yeah, so please feel free to leave if you are ready to go.
Thank you.
Thank you. Bye, Zach.
Thank you very much.
Thank you, Gabriel. Thank you. Wow, I see so many thank you in the chat box. Okay, so I guess we have no questions to discuss right now. I'll share the recording online, and also I'll share the slides of everyone on CCLE, so that if you want to check out other details of other people's work, that will be a great chance. Thank you. All right, so thank you and have a nice winter break and happy holidays in advance. Thank you, bye.